Good afternoon, everyone. Welcome to this afternoon's Snap Revise web class on GCSE Physics Thinking Distance. And I'll go through what we're going to be covering in just a moment. So just to introduce myself, if you've not been to any of my sessions before, my name's David. I'm a GCSE physics teacher, and I've been teaching for about 18 years now, in fact. And I also examine for AQA, Edexcel, and OCR. So I'm fairly familiar with how the exam boards require answers to be given and the kind of format and the kind of pitfalls that students can fall into. So today we're going to be looking at thinking distance, and the objectives are to understand the definitions of reaction time and thinking distance, understand what factors affect thinking distance, understand the definition of stopping distance and how it's affected overall by the speed of a vehicle. We're not going to be calculating braking distance, but it may come up in conversation. And obviously, if you have any questions, then please pop them in the chat and I'll do my best to address them as we go through it. So key ideas for today are things like reaction time, thinking distance, which is the distance a vehicle covers during the driver's reaction time. And we're going to be looking at factors that affect that when you're driving a vehicle. And we'll look at stopping distance, how it's affected by speed and so on. So just to have a quick look at the specification, AQA says this about stopping distance. It's the sum of the distance the vehicles travel during the driver's reaction time and also the distance it travels under a braking force. Sometimes I've seen students say when they're asked a question, what factors affect the braking distance of a car? They've said how hard you press the brake pedal. Don't say that. It's always assumed that maximum braking force is being applied when a vehicle is under braking force. Hi there, Alfred, and S there, hello. And then furthermore, it talks about reaction times varying. We'll talk about why that is the case. And you need to be able to estimate typical reaction times of human drivers and interpret and evaluate measurements. Edexcel, very similar, explain methods of measuring human reaction times. Hi Josh, and recall typical results. So making those estimates, maybe the reaction time of a normal healthy human, it's about 0.2 of a second. Recall that the stopping distance of a vehicle is made up of the sum of the thinking distance and the braking distance added together, and describe the factors affecting a driver's reaction time, including drugs and distractions in the vehicle. OCR, again, very similar as the other two, explaining methods of measuring human reaction times, recalling typical results, particularly using a ruler drop experiment to estimate a human's reaction time, and explain the factors which affect the distance required for road transport vehicles to come to rest. So what do we already know about reaction time? Let's start here. So the equation for distance, as we already know, is distance is speed times time. So we'll start at that point. Distance equals speed times time. And here on the right hand side, we've got a velocity time graph, sometimes called a speed time graph, but more correctly, velocity time graph. And the area underneath the velocity time graph is quite useful to us. So if we just shade in that area there, the area underneath that velocity time graph from where it starts to where it ends is equal to the displacement. And the displacement is the total displacement, if you like, the distance traveled by that vehicle during the time t. So we can calculate that area there using the formula for the area of a triangle. It's really straightforward with this one. So it's just half height times base. So the area under a velocity time graph is the displacement of a moving object. Sometimes these distance time graphs get a little bit more complex. They might have a little flat area in them. So you might have something that looks a bit like that, and then a bit of a rise and then a fall. And the way you work them out is you just split them up into triangles and squares. and you work out the area of nice easy geometrical shapes. So 2 squares in this case I'm drawing here, and then 2 triangles, and you could sum them together to get the total displacement of that object. Aisha Shika, nice of you to join us, thanks. And we've got quite a few people watching today, which is excellent. Any questions, please just pop them in the chat and I'll try and deal with them as we go. So let's now move on and talk about reaction time and thinking distance. So the reaction time is the time between a person noticing a stimulus, detecting a stimulus, and acting a response to it. So it's the time between detecting a stimulus and the person's response to it. So, that could be a cat running across in front of a car. You see the cat, there's a short period of time where your brain processes the information and then you respond by applying the brake. And from person to person, reaction times will vary. Hi, Sharon. So from person to person, reaction times vary naturally, and they're also caused to vary by different factors we'll come to in a minute. Different people react at different rates to different stimuli, but a typical value of reaction time could be 0.2 seconds for someone who's very fast, maybe up to 0.9 seconds. Just to recap, a stimulus here means anything that could cause a reaction. So like I mentioned the example of a cat running across the road. Excuse me, it could be a flashing light, a loud noise, a traffic light changing, person running out in front of you, things like that. They're all examples of external stimuli. And as you get older, your reaction time will naturally increase. So the 0.9 second reaction time here could be that of an older person, and 0.2 seconds there could be that of a much younger person. Now we can measure reaction time, and a simple method of doing that involves just dropping a ruler near someone's hand and seeing how far down the ruler they're able to catch it. So just to make a note on that, so this involves dropping a ruler above someone's hand and seeing how far down the ruler they catch it. And the further the ruler falls before they're able to catch it, the slower the person's reaction time. So the shorter reaction time means the ruler will be caught nearer to the bottom. It'll be caught quicker. A longer reaction time, well, if you're really bad, the ruler falls straight between your fingers and you don't catch it at all. This is a typical experiment that's often carried out in classrooms, and you may be required by the exam board to describe a simple method to measure reaction time, and this is a good example of how you can do that. You could also use a computer or an electrical circuit that measures the time between a stimulus and a response. Yeah, thank you, Samaya. Yes, you said, could you also talk about clicking a mouse when the screen color changes? Absolutely, you could use a computer in that way. You could use any kind of external stimulus, someone holding up a flashcard and you pressing a buzzer. You could use some form of timing device, which will automatically detect someone's reaction time, moving to a switch, or yeah, as you say, clicking a mouse on a computer when a screen changes color is a very simple one and a very good one. Okay, you can also, in this experiment, using your knowledge of gravity and how objects fall under gravity, you could actually put a scale on the ruler, which puts a scale on in seconds or milliseconds rather than distance as well. So moving on to thinking distance. So we've talked about reaction time. And now we'll talk about thinking distance, and be careful not to confuse thinking distance and reaction time. Some students confuse the two and start talking about thinking time and reaction distance and so on. The thinking distance is the distance a vehicle will cover during the reaction time of the driver. So when a driver spots a hazard ahead, the driver will take some time to process that information from that stimulus before responding and before putting their foot on the brake. And as I said earlier, these are all relating to sort of an emergency stop situation. So it would always be full braking force or no braking force. And the thinking distance is the distance the car or the vehicle travels during the driver's reaction time. So for a given speed, a longer reaction time means that there will be a longer thinking distance. So when something appears in front of a car while someone is driving, like an animal or a person, the driver will put their foot on the brake, but it doesn't happen immediately because of the reaction time, giving rise to this thinking distance as we process the information and think about what we're going to do. The signal has to pass from our eyes to our brain. The brain has to process the message, send signals to the muscles in your foot, telling it to push the brake down. So while you're thinking, the car is still moving, and that distance is called the thinking distance. So let's look at factors that affect the thinking distance. So the first one there is drinking alcohol. Although the legal limit of alcohol is set quite low, I won't quote it in case I get it wrong, but it varies what one can actually have in terms of alcoholic drink before you exceed the legal limit. But recommendations and studies have shown that even a very, very small amount of alcohol will have an effect on your reaction time. So even if you're within the legal limit, your reaction time will still be slightly longer, and so your thinking distance will extend. So you are still driving less safely than if you haven't drunk any alcohol at all. Drugs, medicines and drugs can also affect your thinking distance. Prescription drugs and medicines, as well as other drugs and medicines. So depending on the type, they can extend or maybe in some cases even shorten your reaction time. But many drugs, particularly painkillers, can extend your reaction time and therefore increase your thinking distance. If you're tired, then your brain is going to take longer to process any external stimulus. So that's going to increase your thinking distance because it's going to extend your reaction time. Any distractions like using a radio in the car, using sat nav, mobile phones and so on like that. Even though some of those things are legal to use in a car, if you are distracted whilst driving in any way, that's going to extend your thinking time, your reaction time, and therefore your thinking distance. And then also being distracted by others in the vehicle. So if you have distractions within the car, maybe an animal, a dog that maybe isn't strapped in properly, or loud discussions, arguments, they can extend your reaction time and your thinking time. Yeah, distractions will cause or can cause an accident. Anytime you're not focusing entirely on the road ahead and your brain isn't quickly processing all the information it's receiving, you might miss something or delay your reaction and cause an accident. And also eating or drinking is also a distraction, of course. If you're eating or drinking in a car, I have actually heard, whether it's true or not, I don't know, of someone who's been prosecuted for eating an apple behind the wheel. So it was deemed that it was distracting them from being able to control their vehicles safely, which it might well have been. So drugs and medicines, not just illegal drugs, but also prescription drugs. You need to check, read the labels of things to make sure it's okay to drive while you're taking it. Some medicines make you drowsy, therefore increasing your reaction time and thinking distance, and eating, drinking, radios, phones, and so on. And we've covered all the things that you might want to say when you're asked to state anything that affects thinking distance. So let's look at calculating a thinking distance. So here we've got, let's have a look. Lahey, I meant watching another car accident as passing by. Oh yes, of course. Yeah, it's a common habit of people, unfortunately, on the roads to what we call rubberneck, and is to look at anything else that seems to be going on that's more interesting than what's going on in your own car. So people will look at accidents that have happened. They'll look at police cars that have stopped someone by the side of the road. And that distraction can also lead to further accidents. Yeah. So let's look at calculating thinking distance. We're asked here to estimate the thinking distance of a car traveling at 14 miles an hour. And there are 1,609 meters in a mile. So we've got a little bit of calculation to do here. Miles per hour is not a standard unit, it's not an SI unit. So step one is to convert the speed into meters per second. So speed is going to be equal to the number of miles per hour, 40, times the number of meters in a mile, so 1,609. We're given that information in the question. And then we need to divide that by the number of seconds in an hour, because we want meters per second. So seconds in an hour is 60 minutes, each 60 seconds long. 60 times 60 is 3,000, sorry, it's not right there, 3,600, there we go. So 40 times 1,609 divided by 3,600. Hi, Saba. Welcome. Look, you're coming for a long way away. That's always good. Yeah, we have people coming and joining us on these sessions from all over the world, from the UAE, Dubai, Pakistan now as well, I know, in America and so on. Okay, so we do that calculation. We work out the speed is 17.9 meters per second, and we're giving that answer to one decimal place. We've got one significant figure in the 40 miles per hour. We've got four significant figures in the meters per mile. The one decimal place is a reasonable level of accuracy there. So step two then, to calculate the thinking distance, is we need to start off by estimating the reaction time of the driver. So we can pick a number between our estimated range of 0.2 to 0.9. We're going to assume that, let's say 0.2 seconds is the reaction time of this driver. You could pick any sensible number, so anything in the range of about 0.2 to 0.9. As long as you do then the calculation correctly after that, you'll be fine. And then the second point we need to do for step two here is we need to understand our distance equation. So distance is going to equal speed times time. Distance equals speed times time. So our thinking distance, using that formula, is going to equal our speed in meters per second, which we've just calculated. So 17.9 times the time it takes us to respond, which we've decided is going to be 0.2, and that's an estimate. So 17.9 times 0.2, and that equals 3.6 meters. So if you're driving a vehicle at 40 miles an hour, and it takes you a fifth of a second to respond to an external stimuli, in that time, you will have traveled a further 3.6 meters before you've even begun to put your foot on the brake. Okay, so just a quick understanding check at this point. Be really helpful if you could pop in the chat for me a 1, 2, or a 3, depending on how confident you are. Excuse me. So if you're finding it all straightforward, just give me a 1. If everything's okay, most of it's clear, give me a 2. If you're confused about anything, then apart from just giving me a 3, please ask questions as well if there's anything you want me to go over again. Okay, thanks very much. I'll keep an eye on the chat. If anything other than a 1 appears or a 2, I'll come back to you. So let's have a go at putting some of this into practice, have a go at some questions. Thanks, Saba. Thanks, Josh and Sumaya. So this question is asking us to complete a sentence by putting a cross in the box next to your answer. Thanks, Lahey. If there's anything in particular that isn't clear that you'd like me to cover again, do just pop it in the chat. The driver's thinking distance is most likely to increase when which of these? So the driver is tired, there's ice on the road, the car is heavier, or the car moves at a slower speed. Which of those four is likely to increase the thinking distance? Sabra, I hope you're not having a problem with seeing the slides. Everything appears to be clear where I am. It could be down to a connection glitch if that is the case, but I can't see anything wrong at this end. So we've got a number of different answers here. We've got a D and an A. Okay, let's have a look at D and A. Well, driver's thinking distance is most likely to increase. Now, if the car's going slower, whatever their reaction speed, the thinking distance will decrease because the car won't be going as fast, it won't cover as much distance. Yeah, so A is the correct answer here. A is the correct answer. The driver's thinking distance is most likely to increase when the driver is tired. Yeah, Lahey, I understand. And they do sometimes do that too in exams. They'll give you a non-SI unit because it's the everyday language used. When we talk about speed, we usually talk about, well, in England, miles per hour or else kilometers now, perhaps. But when they do that, they will give you a conversion factor. It's just giving you another step of work to do, which would usually be rewarded by an additional mark. So just be careful that you don't miss that if they do throw in a conversion needed for a calculation. But equally, if you do miss it and you do a calculation, assuming everything is given to you in SI units, then if that calculation is correct in every other way, you may well still gain a mark or two. You just won't be able to gain full marks because you didn't do the conversion. Let's have a look at another question. Here we have a local council has reduced the speed limit from 30 miles an hour to 20 miles per hour on a few roads. The reason for reducing the speed limit was to reduce the number of accidents. A local newspaper reported that a councillor said it will be much safer because cars can react much faster when driving at 20 miles per hour than when driving at 30 miles per hour. And then the question states that this statement is wrong and why. So this is for 1 mark. You've got to state why is this councillor wrong in stating that cars will react quicker at 20 miles per hour. Again, it's a typical example of how in everyday speech, science gets a little bit misquoted or gets a little bit wrong. So why is that wrong? I'll give you a moment if any ideas, if you want to pop any ideas in the chat, I'll get on and give you the answer in just a second. So we're only changing the speed of the car. We're not doing anything about the people who are driving the cars. So to state that the drivers react much faster when they're going slower is completely incorrect. The reaction time of the individual drivers is not going to be any difference. What will change is the distance the cars travel during the reaction time. So the thinking distance will be shortened, which means that at 20 miles per hour, if someone runs out in front of you, if you're passing a school perhaps, you're much more likely to be able to stop before an accident occurs because you're not going as fast. Yes, the speed of the vehicle has nothing to do with reaction time, Samaya, absolutely right. So that's the answer, and it's only 1 mark, so you just need to state exactly what you've just said, really. Reaction time of the driver does not depend or is independent of, does not depend on the speed of the car. And there's your answer for 1 mark. Just picking out the science from a statement. Stopping time will be faster if you're going slower. That's true, but it's not something that this particular councillor or newspaper is reporting. A councillor has actually said. They're not talking about stopping time. So here they're saying the drivers will react quicker. No, they won't, because the speed of the vehicle doesn't affect reaction time. Let's move on and have a look at a question with some graphical data in it. So we've got two graphs here, one for car A and one for car B. The graphs show how the velocity of two cars, A and B, change from the moment the car drivers see an obstacle blocking the road. So both cars, to begin with, are travelling at 15 meters per second. So we go 15 meters per second. They both start at that same speed. How does a comparison of those two graphs suggest the driver of car B is the one who may have been drinking alcohol? One of the drivers has been drinking alcohol, the other driver is wide awake and alert. So which one of these two graphs suggests their driver has been drinking alcohol? So you'll notice that the slope of the graph once the driver has applied the brakes is the same gradient for both. So the cars are identical in their braking behavior, but which driver takes longer to react? And that is going to be car B's. So car B's driver has a longer reaction time. And we can suggest that he may have been drinking alcohol because alcohol will have this effect on someone's reaction time. Okay, excuse me. And as I mentioned earlier, the area underneath the line on a velocity time graph will actually tell us the displacement. So if we look at these graphs, you can see that the total area under the under the 15 meter per second part of car B's journey, that area is much bigger than the area there. And we're going to come to that point in just a moment. Okay, moving on from there, let's look at stopping distance overall. So stopping distance is made of two things. The braking distance is something we need to talk about first. So we've been talking about thinking distance, now move on to braking distance, and that is the distance a car travels while the car is being stopped by the brakes. So when a person puts their foot on the brakes, the car will travel a certain distance while the brake is applied until the point at which the car stops. And the braking distance is the distance the car travels while the car is being stopped by the brakes. We will cover braking distance more in a later revision session, so don't worry too much now if you don't get that entirely. Stopping distance is the total distance that a car travels from the moment the driver sees an external stimulus until the car is stationary. So I'm just having a quick look in the chat. If the driver drinks, does it have an effect on the speed? It might well do, because drinking alcohol and driving a car, drinking alcohol will affect the judgment of the driver. So they may well be driving faster or even slower if they're not confident. So it will do. But the most important effect that alcohol has on a driver of a vehicle is decreasing their ability to react quickly. So increasing their reaction time. Back to stopping distance. So we've covered what braking distance is. Stopping distance is the total distance that a car travels from the moment the driver, sorry about my handwriting there, from the moment the driver sees danger until the car is stationary. And so stopping distance is the sum of thinking distance and braking distance. So the total stopping distance of a car is the thinking distance of the car plus the braking distance of the car added together. Let's have a look at a diagram explaining this. So here we have a driver driving along a road. We've got a couple of points here marked on our diagram and someone on the road walking a dog. So at this point in time, the first point here, the first arrow, is where the driver spots the danger. The driver has seen that there is someone walking a dog in the road in front of them. So they have to think, they have to respond, they have to process that. So yeah, the first part there, Sabra, is the thinking distance here, correct? So this first piece of the distance covered is the thinking distance. And then after the processing time of the driver, after their reaction time, they then apply the brakes. So the brakes are applied here at the second arrow. And then the second portion of the stopping distance, which is the overall distance the car takes to come to a stop. I'll label that here. The second portion of that is the braking distance here. And then the car is stopped by the time we get to the end of those two distances added up. So the driver initially spots the dog, sees the danger, and they take a little bit of time to process the information, apply the brakes. The distance initially is the thinking distance, then they apply the brakes, and that then gives us the braking distance before the car comes to a halt. And the total of the two, the braking and the thinking distance, is the stopping distance. Now, clearly, if the driver was inhibited by alcohol, had a longer reaction time, there is a greater chance that they would actually cause an accident because the thinking distance would be extended. And the speed of the vehicle, if the driver is driving faster and is alert and with the same with the same reaction time, if the vehicle's faster, then the thinking distance will be longer. And the braking distance will also be longer. And not in quite the same way, but we'll come to that in just a moment. Okay, so for a given braking force, the greater the speed of the vehicle, the greater the stopping distance. This is something pretty much out of the highway code. Oops. Sorry, my pen back. Excuse me a moment. There we go. Okay, so for a given braking force, the greater the speed of the vehicle, the greater the stopping distance. So at 20 miles per hour, we've got a thinking distance of 6 meters, and then we've got a braking distance of 6 meters. So total stopping distance of 12 meters for the first one there. It's about 3 car lengths if an average car is about 4 meters long. And then as we go faster, the next one is 23 meters, and the next one down is 36 meters. And then 53 meters, 73 meters, and 96 meters. And what you can see here on the graph is that the thinking distance, that's going up proportionally to the speed of the vehicle. But the braking distance is increasing ever more with speed. And that's because the speed of the car determines the kinetic energy of the car. And because there's a velocity squared in the kinetic energy formula, energy is half mv squared, that means that if you double the speed of the car, you're quadrupling the amount of energy in the moving vehicle. And so the brakes have to change that kinetic energy into heat. So the faster the car is going, the more energy is required to be converted into heat in the brakes in order to stop the car. And if you double the speed of a car, you quadruple the energy. So doubling the speed quadruples the braking distance of a car. So how are we feeling about what we've just covered? So we've just summarized what stopping distance is overall, about the need to add thinking distance to braking distance. We've covered what thinking distance is and how it depends on reaction time, what affects that, and also what braking distance is, the distance a car covers once the brakes have been applied. So if you could give me some 1s, 2s or 3s, I'd be really grateful. Any 2s or 3s, please pop a question in the chat as well. So yeah, stopping distance depends on the speed. If the speed is greater, then both thinking distance and braking distance will be increased. Thinking distance will be proportional to speed, but braking distance will be increasing ever more as speed increases, not proportional. Let's go back to this graphical question we looked at earlier. So the graph is showing how two cars, A and B, change, how their velocity changes from the moment the car drivers see an obstacle. Now, we were talking earlier about which car driver was most likely to have been drinking alcohol, and that was car B. This question, though, asks us to calculate how much further car B travels before stopping compared to car A. So what we need to do is look at the graphs, and we need to remember that the distance under a velocity time graph is displaced. Sorry, the distance can be found by finding the area under a velocity time graph. So distance is the area under the velocity time graph. So we look at the two graphs, we look at car A. Car A, we're going to look at this area here, trying to draw that as neatly as I can. So we have a rectangle there representing the thinking distance of car A. And then for car B, we have this area here representing the thinking distance of car B. Now the area under both of the triangles is the same because the cars are braking in the same way. So the difference in the time to stop here is entirely down to the reaction time and thinking distance of the cars. How much further does car B travel? Well, the area under the straight part of the graph here for car A is 15 meters per second times 0.6 seconds if we look on the graph scale on the x-axis there, so times 0.6. So the car A distance is 15 meters times 0.6, and then we could add on the area under the triangle we wanted to, but it's actually only asking us to calculate how much further car B travels. So we only really need to look at the area under the rectangles. And for car B, the area is going to be 15 meters per second times, in this case, 1.4. And so moving on from there, if we look at the actual difference in the distances, we can see that when we multiply 15 by 0.6 and 15 by 1.4, the difference in the distances between the two is going to be 12 meters. So car B travels 12 meters further. The stopping distance is quicker for car, is reduced for car A because they are reacting faster and have a shorter thinking distance. Let's have a look at another question. So this one, the stopping distance of a car is the sum of the thinking distance and the braking distance. Table 4 shows how the thinking distance and braking distance vary with speed. And the data refers to a car in good mechanical condition driven by an alert driver. Explain why the stopping distance of the car increases if the driver is very tired. So why will the stopping distance increase if the driver is very tired? We've got to get 2 marks for this, so we've got to make 2 points. So what can we say about tiredness? Tiredness increases reaction time. There's 1 mark. We've clarified, we understand that the reaction time is going to increase. Longer reaction time. Yep. Longer reaction time increases the thinking distance. Therefore, stopping distance increases. You wouldn't have to make this last point, I'm just making it completely clear. So your 2 marks would come from making those 2 points there. Tiredness increases reaction time, and longer reaction time increases thinking distance. Yep, thank you, Molly. That's right, driver is not as alert, so the thinking distance is increased. I think you would still need to make a point about reaction time, so you would get 1 of the 2 marks for saying that. Do make a statement about how being tired increases reaction time and therefore increases the thinking distance, and then you make sure you get the 2 marks. So let's have a look at this question in a slightly different way. Next part of this question. The student looks at the data in table 4 and writes the following. So this student is saying that thinking distance is proportional to speed. So these are our thinking distances, and they're saying they're proportional to speed. They're also saying that braking distance is proportional to speed. Is the student correct? So let's have a look at the numbers. So 10 meters per second, the thinking distance is 6. If we add a third to the speed, go up to 15, then we add a third to the thinking distance, goes up to 9. And we've got a difference that's increasing steadily each time. So we've got a difference of 3, 3, 3, and 3. So the first statement of the student is correct. But what about the second statement? Braking distance at 10 meters per second is 6. So at 20 meters per second, we'd expect it to be 12, but it's not. It's actually 4 times 6. So doubling the speed quadruples the braking distance. So the second point the students made is incorrect. So we can state, first of all, that the student is incorrect. Thinking distance is proportional to speed. But braking distance is not. We can see that by looking at the data in the table. And because we've looked and used the data in the table, we should give some examples of data from the table to make sure we get the marks. Although it's only a 2-mark question, if there's data given to you, it's normally expected that you give some examples. So let's give an example, e.g. increasing speed from 10 to 20 meters per second. That doubles the thinking distance. But it quadruples the braking distance. And that just demonstrates that we've looked at the numbers in the table, we've looked at the 10 and the 20 speeds, and we've drawn some conclusions from that. Okay, Lehay Saint is just making a comment that distance is the area of a trapezium. Yeah, you can use the trapezium rule if you want to calculate the area under a velocity time graph. I find the easiest way that students do it, and the way that they get least confused, because not everyone is as mathematically able as others, is just to calculate the areas of every rectangle, square and triangle within the area under the curve. So just split up a more complicated curve into rectangles, squares and triangles, and then calculate those areas and add them up. Okay, so hopefully we now have covered everything we needed to cover for stopping distance today, and you should be able to understand the definitions of reaction time, the time taken for the driver to respond to an external stimulus, and thinking distance, which is the distance covered during that reaction time. Understand what factors affect thinking distance. We put together a table of the various things, distractions, drugs, alcohol, etc., which do that by extending reaction time, and understand the definition of stopping distance, which is thinking distance plus braking distance, and how it is affected by the speed of a vehicle. So it's time to ask you now if you have any further questions for me. So if you've got any questions now, please pop them in the chat, and I'll come back to anything you'd like me to cover. So that's correct, Lehay Saint. Stopping distance is thinking distance plus braking distance. If you have any questions, please pop them up. I'll keep my eye on the chat for the next few moments in case anyone's typing. And while I'm doing that, and if you're doing that, I'll just recap that although I don't have a slide to show you this, we do have some upcoming classes. So let me just recap when they're going to be. So we have a chemistry revision class on tests for gases on the 16th at 4 p.m. We have a maths web class on straight line graphs on the 30th at 3 p.m. We've got my next physics web class on changing atomic models. That's going to be on the 6th of February at 3 p.m. And then we have an electrolysis chemistry web class on the 20th of February at 4 p.m. Okay, that's great. Thank you very much for being with us all of you today. And thank you, Samaya. You're very welcome. And I hope that's been of use to you, and enjoy the rest of your day.